Good morning. Let's continue on the Fourier series, okay? Okay, so I think I showed you what the Fourier series looks like, okay? But before we look at the detail, the calculation, so just want to cover a few simple concepts before we start look at the Fourier series carefully, okay? So first concept is called orthogonal functions. Basically, if we consider the following set, so 1 cosine omega naught t, sine omega naught t, cosine 2 omega naught t, and sine 2 omega naught, and up to maybe cosine m omega naught, and then sine m omega naught t. Okay, so there are infinite, basically, sine, cosine terms in this set of functions. And in this case, the base period, you look at this one, this is the base period of the function, which is 2 pi over omega naught. So that's the period of that function. And we can show the following properties like that, okay? And we can show that they are orthogonal they're orthogonal over a period t naught. So orthogonal, if you recall that essentially when you're integrating the multiplication of any two of the functions together over the period, then you get 0, right? That's what the orthogonal basically means. Okay. But I can show following things here. So for example, if I integrate from half of t naught over half of t naught to negative half to positive half, integrate, let's say for example, sine n omega naught t. Okay. So this is like 1 times any one of the sinusoidal signal here, dt. Okay. Sine is a periodic function, and this is equivalent to integrate 0 to t naught, and they turn out to be 0. So basically the total area underneath the sine is 0, right? Yeah. And similarly, if you do integral of cosine, and you also get a 0. Okay, so that basically this one says between 1 and any other function, they are orthogonal. Right. And then how about if you integrate between any two of the cosine terms? So let's say we integrate n cosine omega naught t times m times m omega naught t, cosine m omega naught t. Okay, if this is a 1, what does it equal to, right? So I'll show you this one here, okay, and then I have a couple more, and I don't gonna show it everything else anymore. Okay, so when you have two cosine terms multiply each other, you can make use of this property. So cosine A cosine B, okay, equal to cosine A plus B plus cosine A minus B divided by 2. Okay. So this trig identity. because cosine A plus B equal to cosine A cosine B minus sine A sine B, and then this one is cosine A cosine B plus sine A sine B, right? So you get 2 cosine A cosine B divided by 2, you get this, right? So let's use that identity to apply to these integrals here. I have a cosine, so A plus B is this plus that, so which is m plus n omega naught t, and plus cosine m minus n omega naught t, okay, and then divided by 2. Okay, so this is all in the big bracket at dt. Okay, good. So from here, you need to basically be a little careful here, right? If m equal to n, okay, if m equal to n, then the first term becomes basically cosine 2m, for example, omega naught t. Second term becomes cosine 0, right? Divided by 2, and 0 to t naught dt. The integral of a cosine over a period, it has to be 0, right? Because it's the area underneath the cosine, okay, it's going to be 0. And this cosine 0 is 1, so the integral of the second term is t naught over 2. So the overall is t naught over 2. So that's when m is same as t as n. But if m is not the same as n, so these two, and this is not 0 and that's not 2m, then this integral becomes, right, so you can integrate the two cosine terms separately. So integration cosine is sine, right? So basically get the integrand, okay, the integration results, you get a sine m plus n omega naught t, and then you have m plus n omega here, so m plus n omega naught, okay, divided by this. Okay. So the derivative of this give you back this. And don't forget the 1/2, okay, at the beginning here. Second one, you get sine m minus n omega naught t minus m minus n omega naught. Okay, so the integration of these two terms, you get this. And then you plug in 0 to t naught, okay, plug in this limit set here. And t naught, don't forget, is 2 pi over omega naught. So once you plug it in, t naught, which is 2 pi over omega naught here. So omega naught cancel out. You're going to get a 2 pi times this, 2 pi times this. So sine multiple of a 2 pi will always be 0. So both of these terms will be 0. So you get a 0 here. Okay. So basically, this integration, okay, when you pick two cosine, multiply together, integrate over a period, okay, you get either 0 or t naught over 2. When m is not the same as n, you get a 0. When m is same as n, you get the t naught over 2. So again, it shows the orthogonal property, right? As long as n and m, as long as you're not dotting each other, essentially. Okay. Remember, the orthogonal is like a dot product of two vectors. When you use two perpendicular vectors dot each other, you get 0, right? Yeah. So that's a proof here. Okay. And I want you to try a similar integrations here to show orthogonal. If you're going to do the sine in omega naught t and cosine m omega naught t dt. For example, you pick a sine and you pick cosine. Okay, then you multiply them together. Okay, integrate over one period. This one is a straight 0. There's no ambiguity here. Again, this shows you these two are orthogonal to each other. Okay. And also, if you do two sine terms, and you get similar results. When m is not the same as n, is 0. When m is same as n, you get t naught over 2. So what I showed you here is the property of orthogonal function, right, for this set of trigonometry functions. Okay. So these trigonometric functions, sine, cosine, including the constant 1, they're all orthogonal to each other. Except orthogonal, they don't orthogonal to themselves. Right? That's basically what it means. Okay. All right, so that's one fact. Okay. There are some other facts that could be useful to our understanding. Okay. So let me write down some other facts. I may not write all of them. I do have a lot of them in the lecture notes, but I wanted to write down some of them. First one, if f of t, okay, has a period of t naught, okay, or t, okay, let's see, this one has a period of t, then for any number a, okay, then you can, if you're integrating this function, okay, from 0 to t, it's equivalent to shift the integral by the any number a. Okay. So that's a nature for periodic function. Okay, so this is a fact that can be useful. And the other thing is, if f of t equal to f of negative t. Okay. So I think in the first lecture or first tutorial, I can't remember now, we probably went over a little bit about this. So when you have f of t equal to f of negative t, right? This one basically says f of t is a even function. Okay. Okay, it's even. Even basically means it's symmetric to the vertical axis. Okay, either the y-axis, right? So, for example, cosine t is even. Okay, there are a lot of even functions. X squared, and then let's use a t squared. T squared, it's an even function. Okay. So that's the concept of even. Now, if f of t equal to negative of f of negative t, okay, or f of t plus f of negative t equal to 0, okay, then we see that this f of t is an odd function. Odd function means it's a function symmetric to the origin. Okay, so not symmetric to the y-axis, it's symmetric to the origin. And sine t is an odd function. If you plot sine t, this side is here, and then this side is here, right? So it's symmetric to the origin here. Okay. So that's odd function. Some other examples of even or odd. Okay. So, for example, if I have f of t equal to t cubed, Is it an even function or odd function? It's an odd, right? Because you can test this, right? F of t plus f of negative t equal to 0, then it's odd. If I have f of t equal to t to the power 6 minus 1 to the square root 1 minus t to the power 4. Okay. This one, right? The power here is all even numbers, so this one is an even function. So when you plug negative t into this one, you get back exactly the same function. This odd and even can sometimes simplify your calculation, your integral calculation, quite a lot. Now, I didn't mention in single function integrals, when you integrate, especially over a certain period for odd and even, you can simplify the situations. Same rule actually also apply to double integrals. So anyway, so that's a little beyond the topic here. The product of an even function and an odd, okay, if you multiply an even function and odd function together, it produces an odd function. Okay? Yeah. And if you multiply even and even, it gives you an even function. If you multiply an odd and an odd, it gives you what? An even function. Okay. And derivative of a even function. Okay. When you take a derivative even function, and you get an odd function. Right, that's pretty interesting. But if you take derivative an odd function, you get an even function. Okay, so they get even. Yeah. And now, if you're integrating, okay, let's say if f of t is odd, okay, if f of t is odd here, and if you're integrating from negative number to a positive number, okay, for this f of t, okay, then you get 0. Okay, so a good example is also always a sign, right? If I integrate from negative pi to positive pi, the area underneath the sign is 0. Okay, so that's the nature of the odd here. Okay. Now, if f of t is even, okay, if it's an even function, and then if we do the same integral, okay, from negative a to positive a, okay, we can show that this is equivalent to 2 times integral 0 to a. So that's even function nature. And good example is always, let's say, use cosine here. Okay. If I integrate, let's say, from negative pi over 2 to pi over 2 for cosine t, so because it's even, symmetric, right? So instead of from here to here, you can 2 times 0 to pi over 2. Okay. So that's even function property. In my lecture notes, I do have a proof of this. Okay, so those are some of the properties I think is relevant to the Fourier series. Okay? And even if it's not relevant, I think those are really good properties sometimes you bear in mind that it can simplify your calculation quite a bit. Okay. Okay, now let's go into Fourier series. Okay. Always remember, Fourier series are an approximation, okay, for periodic functions. So it has to be periodic. Okay? It's not infinite function without a periodic nature. And the idea of the Fourier series, as actually I showed you, is to write a periodic function into a sum of a series of cosine and sine terms with a different frequency. Okay. We call it harmonic, basically, frequency. Okay. So first question is, what is a periodic function? Okay. So let's consider g of t is a periodic function. If its period is t naught, okay? Of course it's not zero. It can be any numbers, or the type of period can starting from zero or even starting from somewhere else. That's fine. Okay. Yeah. So one of the property you got to know is, okay, if this is a periodic function, then the function g of t will not change when you shift it by t naught. Okay, so that's basically the nature of a periodic function. So if you shift it by t naught, it doesn't matter how you shift, whether it's a positive or negative. So even negative is also okay. 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 So one of the thing for you, one of the ability, right? If I give you a function, a graph, you need to be able to identify t naught from a graph. Okay, that's a very basic expectation. If I give you a periodic function sketched out on the paper without telling you the period, you have to be able to identify this t naught from the graph. So this is what I mean, and here very simple. So let's see if I graph a g of t. Okay. Let's say you have a graph showing like this. What will be the t naught? Because you need the t naught to calculate the rest of the computation. 2, yeah. Repeats, right? How do it repeat? So t naught is 2. It's not 1, eh? You heard somebody say 1. Yeah. So unfortunately, if you identify this wrong, the rest of the computation will be all wrong, right? So this is something that you have to practice to make sure you got your t naught right. Okay. So now let's look at what is the Fourier series for a periodic function, okay, a signal. The Fourier series for the g of t, okay, is defined as the following formula. So g of t equal to a naught plus equal to this. That's g of t. using Fourier series. So when you finish this lecture, or when you finish today, have a break, grab a piece of paper. Okay, even though you will have the formula, I would highly encourage you to write on the piece of paper like just a scribbling. Just jot it down 10 times, 20 times. Okay, yeah. So what you have it here is you have a constant term a naught, and then you have a summation n from 1 up to infinite. Inside the bracket, you have a coefficient a n, b n, each coefficient times a cosine term and a sine term. And the cosine term, sine term, the frequency of that depends on the value of n. Okay. So you have cosine omega naught t, 2 omega naught t, 3 omega naught t, and 4, 5, it keeps going. Okay? Yeah. So now you can see, basically, right, g of t is a sum of cosine and sine terms. That's basically the nature of Fourier series. They express a periodic function into a sum of cosine and sine terms. Right? So that's actually quite interesting, because if you look at this one, this is a periodic function, right? If nobody tells you, how could you know? In the back of these boxes, there are what? There are infinite number of cosine sines at there. Right? That's basically what happens. Okay? So I'll show you a little bit drawing it here to understand a little more. But for now, the question is, what is a naught? What is a n? And what is the b n? Right? The coefficients for the three terms at here. So a n, b n, we call that Fourier coefficients. N equal to 1, 2, up to infinite. And this a naught, we call that DC component. So sometimes a naught we consider as the average value. And the summation sign, the whole sum term, right? The whole sum term, we call that AC component. Okay, called the AC component. You're learning, for example, you're learning. What are you learning? No, actually, you haven't probably. Have you learned AC/DC? You did, right? Yeah. So, for example, right? Let's see if I have a. Okay, a simple one. Okay. Now, for example, this is a periodic function. This square wave, right? It's a square wave here. Okay. So when you have this square wave, and a lot of oscilloscope can give you the AC, okay, so it can give you the DC component actually. Okay. So if you look at this one here, what's the AC? What's the DC component? The DC component for this one is equal to 1. Does it have a? Because it's symmetric here, right? So the AC, the DC at here is actually equal to what? No, 0, right? There is no DC component. But if I look at this one here, what is the DC component for this guy? One half, exactly, right? That's what AC/DC means, right? So this is DC. It's a straight constant value, okay? Now we do have a formula for calculating this one, though, okay? Yeah, and I'll show you the formulas for this, okay? Yeah. The idea is we need to find this A naught, Bn, and An. First, let's look at what's An at here. To find the A naught, here's what we're going to do. We're going to integrate. Okay, we're going to integrate this periodic function from 0 to its period t naught. Okay, so let's do that. So essentially, see, this is your g of t, right? So I'm integrating both sides, okay, from 0 to t naught. Okay, that's what I'm doing. So if we do that, then we get 0 to t naught a naught dt. That's the first term, integration. And then second term is the whole summation. So you can certainly move the integral into the sum term. And then an cosine n omega naught t plus bn sine n omega naught t dt. Okay. Right, if you integrate both sides of gt, right, this is what you get. And this is where we make use of the orthogonal property, right? When you integrate cosine n omega naught and the sine n omega naught according to the orthogonal property, the whole thing over here should equal to 0. So you only left with this integral, which is a times t naught, a naught times t naught. So which means the a naught equal to 1 over t naught and integration of the periodic function from 0 to t naught. Okay, so that's a naught. Okay. There. So we got one done. How do we find the a naught? Now let's look at how to find an and bn. Okay. Now this is the part I'll skip proof it here. You can take a look at the lecture notes how to find an and bn. Right. So to find an and bn, for example, okay, to find an, I won't show you the detail, but this is what you do basically. You integrate g of t times cosine. Okay. Anyway, let me skip this. It's going to take too much time. I want you to look at the lecture notes here. Okay. Yeah. I like the word similarly, so I escape a lot of details and let you do the work. So an equal to this. So this is the formula for an, and bn is this, and n equal to 1, 2, up to infinite. Okay. So although you will have the formula, but I do encourage you to write this on yourself at least 10 times. I'll guarantee when you're writing it, you actually somehow you will get some kind of inspiration somehow. Okay. Okay. When you look at these three integrals, they're really nothing too complicated. They're just integrals, right? Yeah. They involve the integrations of the periodic function times a cosine. Okay. Sometimes some examples that you will see involves the trigonometry substitution rules. Okay. But a lot of time it's not that complicated. Okay. My expectation, right, is of course to understand what the Fourier series is. So we'll have a different form. But most important is, if you're given periodic function, how do you find a naught? How do you find an? How do you find the bn? Okay, that's basically making application of the three formulas here. Okay. So let me show you a few examples. So for example, let's use that periodic function that I sketched on the top over there. Okay. So let's say this is a periodic function here, okay, with 1 over here. And I want you to find the Fourier series for this function. The Fourier series. So I'm going to basically apply the 3 formulas here to calculate A naught, AN, and BN. First step, identify the period of this function. Of course, is 2. So then omega naught is 2 pi over T naught, which is pi. So those parameters are the one that you use to calculate the integrals. Okay, once you find it, okay, you can rewrite the Fourier series you want, but otherwise, you can just do the calculation. So A naught equal to 1 over T naught, 0 to T naught, g of t dt. T naught is 2, so that's 1 over 2. That's 0 to 2. So what are we integrating? We're integrating from 0 to 2. So from here to here, right? That's 1 period. Within this period, as you can see, your g of t, you're integrating g of t, right? Your g of t, part of that is 0 between 1 and 2. Part of that is 1 between 0 and 1. So this integral really is just 0 to 1, right? And within that interval, the g of t's value is 1. So the overall, you get 1/2. Okay? And that's exactly what I showed you, isn't it? The DC component, this DC is 1/2. Okay, let's take a look. The AN is T over T naught, 0 to T naught, g of t cosine n omega naught t dt. Okay, that's AN. This is the term associated with the cosine term. Replace the t with 2. So replace the 2 with 2, and then g of t cosine n omega naught t. Okay. Replace the omega naught. Omega naught is pi, right? So we replace the omega naught with pi. Okay. Now let's go back to the diagram. When you're integrating from 0 to 2, the only meaningful part of the integral is 0 to 1, and within that interval, the function g of t is 1. So basically you get 0 to 1 and here, which is 1 and here, cosine n pi t dt. Okay, so that's what you get. Now the more you do, you actually will become more comfortable. This one you'll find out to be 0, but otherwise you can still do the integrals here. The integral of this term give you 1 over n pi. Oh boy. How does this happen to that? Okay. So this is 1 over n pi sine n pi t, and then you substitute the limits 0 to 1 in it. So when you substitute 1 into here, you have a sine n pi. When you substitute 0 here, you get a 0. Sine multiple of pi is always equal to So this is why I want you to remember what sine looks like. This is pi, this is 2 pi. Sine multiple pi is always equal to, right? So the whole thing is 0. Okay. Bn 2 over t naught, 0 to t naught, g of t sine n omega naught t. Plug in t naught. Again, you're only going to integrate 0 to 1 and sine n pi t. And this one is 1 over n pi, and negative here, and then cosine n pi t, 0 to 1. Plug in the limits, we get 1 over n pi cosine n pi, 1 minus cosine n pi. That's Bn. Okay. Now you might wonder, is the cosine n pi equal to 0? It's actually not. What's the cosine term? Cosine term is this. This is a pi, this is 0, and then pi, this is 2 pi, 3 pi, right? Okay. So if you look at this, cosine, this n at here start from 1, right? Up to 2, up to infinite. So when n is 1, what's the value? Negative 1. When n is 2, 1. When n is 3, negative 1. So cosine n pi alternate between negative 1 and 1. So this term, you can use negative 1 to the power of n to express its result. And n equal to 1 and 2 up to infinite. So when n equal to 1, it's negative 1. When n equal to 2, it's a 1. In 3, negative 1 again. Okay. That's basically what Bn is. Okay. Or in other words, this Bn, right? If I look at this expression here, when n is odd number, so 1, 3, 5, 7. When n is odd, negative 1 to the power of n is to the odd is negative 1. Then 1 minus a negative 1 is 2. So when it's odd, it's 2 over n pi. When n is even, it becomes 0. Okay? So that's Bn. Right? And finally, you can put all this together and write the g of t out to give you an expression. So what is this g of t, right? So g of t equal to 1/2 plus n at here is odd, and n start with 1, and Bn is 2 over n pi and cosine n pi t as a sine. So that's g of t. You can write down a few terms at here. If starting from n equal to 1, so 2 over pi sine pi t plus n is odd, so then the next is 3, and the next is 5, right? So then you can keep going. So that's g of t. So the original, like unit step type of function boxes or periodic boxes, can be written as a summation of all of this sign here with the coefficients like this. Good? Yeah. So it's a simple example how you can break a periodic function into a summation of sine and cosines. Now, I have a picture I want to show you. There. Okay. If you plot the g of t, which is the black color over here, okay, so the black one is the original periodic function. Okay. Now, if I show you this, if I only plot the first two terms, basically 1/2 plus this term, we get the red sinusoidal here. Okay, so if you want to plot the first one, you get this. And if you plot the first 5 sinusoidal terms, so what does that mean? Basically 1, 2, 3, 4, 5. So 5 terms over there. Then you get the blue color one here. Okay. And if you plot the first 20 sinusoidal terms, then you get the green color curve here. So now you can imagine, right? The more you add, the curve, which is basically the right side expression, will infinitely approach the g of t. Okay. So that's the idea of a Fourier series. You're decomposing a seemingly non-sine cosine term, a periodic function, into something like, okay, an infinite sum of sine and cosine terms. Okay, yeah. So I'll show you a different way of a Fourier series in the next lecture, and maybe a couple more pictures and a couple more examples. Okay. Any questions? One more week to go, and I hope everybody can keep it up. Okay.